Okay, hello everybody. I think we're ready now to start the next session. It is technical paper session D, and this is on optimizing collective operations. We have as the first speaker Tran, who is here beside me. The title of the paper is OHIO, Improving RDMA Network Scalability in MPI All-to-All through Optimized Hierarchical and Internode Communication Overlap Design. Tu is a student at Ohio State University. In fact, all the authors are in the same group that you're probably quite familiar with. In fact, both of the papers in the session are from the Now Lab group at Ohio State University. Tu himself is particularly interested in providing scalable high-performance communication middleware, and he's focusing on optimizing communication within MPI itself. So, Tu, hopefully that's enough of an intro, and you have 25 minutes for the talk, and we'll have 5 minutes for questions.
Right, gotcha. So let me share my screen. Right, I hope you can see it and can hear me well also. Right, so let's begin. Welcome everyone. My name is Tran. I'm with the Ohio State University. So today I will present to you about OHIO, which is a design that can help you improve the RDMA network scalability for auto through a hierarchical design. So let's first start with an introduction. So as you know, we are now in the exascale era, right? And Excel supercomputers, they have powerful CPUs. For example, AMD Milan Rome 2 sockets per node, 128 cores. Intel Ice Lake 2 sockets, 80 cores per node. And all of those compute nodes, they utilize high-performance RDMA networks such as InfiniBand, OmniPath, and Rocky for communication. And in order to exploit such a huge amount of computing power from such a system, we normally use MPI, which is the de facto programming model. And among the communication primitives provided by MPI, Auto is the most communication intensive one. It injects a huge amount of data into the network because everyone talking to everyone. So it's very difficult to scale and optimize due to its global pattern. Scaling Auto on a large RDMA network is not trivial, but we need it because it's not only utilized in traditional HPC applications like matrix transpose, but also in emerging AI DL application like MOE, mixture of expert. So there's the current issue with RDMA network is that it is not scalable. To be more specific, we will see performance degradation in RDMA networks as there are more connections. To understand the reason why, let's first take a look at this diagram. So here you see we can have CPU, we have memory, we have ARNIC. So ARNIC is an abbreviation for RDMA network interface card. So inside an ARNIC, there's a small amount of cache where it stores QPs. So QP is a structure it is used to represent connection. So beside QPs, there are also memory translation table, which store logical physical address so that the ARNIC can access the main memory. So when cache misses happen, the ARNIC will go over the PCIe and access the main memory right here, right? So this overhead will increase the latency and hence affect the performance. Just to give you some idea about how large the cache site here. So in InfiniBand ConnectX 4 and ConnectX 5, the cache size is around 2 MB. For a reliable connection, it consumes around 300 bytes. So as a result, the ARNIC can afford around 5,000 connection that it can store inside its cache. But this number not exactly large, because now that we are in the exascale era, a cluster can have up more than 10,000 nodes, and each node can have up to 100 compute cores. Additionally, several studies have shown that degradation happens even sooner than that, which is to 56 qubits, and this has been confirmed by several RDMA network vendors. So, there are a couple of RDMA transport protocols, and each have advantage and disadvantages when it comes to performance, scalability, reliability. So the first one is reliable connection. RC, this is what we normally use. A process will require a dedicated QP to connect to any remote processes. So it will use a lot of QP, but it's reliable and performance is guaranteed. So for the second design, for the second transport, unreliable datagram. So for this type of transport, a process only need one QP to talk to any other remote process. But for this type of transport, it is unreliable. So we need an extra layer of software for reliability, and hence it will affect the latency performance in general. Another type of transport is DC or dynamic connection. So this one is specific to InfiniBand. It uses the same number of qubits AUD, which is good. It will like scale and can fit into the cache. And DC also is reliable as RC, but there also a catch for this type of connection. There will be some overhead for tearing down as well as establishing a new connection when talk to different processes. So with all of this information in mind, when people design algorithms, they can be generally classified into two classes. The first one is flat. You can think of one simple flat algorithm like Brock. Another class is hierarchical. You have in each node there will be a node leader, right? And the node leader will communicate to remote nodes on behalf of local processes. So we realize that with hierarchical design, there are several benefits, and one of them can help resolve the scalability issue that we demonstrated earlier. So an auto operation, it usually requires an order of n squared times ppn squared number of messages, with n is the number of nodes and ppn is process count per node. The first benefit of hierarchical design is that it avoids the slowdown of inter-node communication by decoupling them. We know that intranode is several times slower than intranode. Intranode is several times faster than internode. So as a result, in flat algorithm like Brock, it doesn't take into consideration of this difference, and it will performance will be bottlenecked by the internode portion. The second benefit of hierarchical design is that it reduces the number of network congestion by reducing the injected message into the network. So as demonstrated right here, we reduce the number of message from n square BBN square to an order of n square. Obviously, the message size will be larger, but we reduce the number of concurrently injected message into the network. The last benefit of hierarchical design is that it will improve the network scalability in RDMA. Because now that each node we will have one process leader, and that leader will communicate on behalf of other local processes. We only need to establish connection from that leader process. So as a result, the number of connections each node we needed reduced from n-1 times ppn to n-1. So here's the proposed solution. In this table, this table summarizes the difference of the proposed design and other existing and state-of-the-art algorithms. So essentially, we propose NOHIO, a high-performance and scalable network-aware auto design. So the proposed design focuses on the small message range. It is hierarchical. It overlaps intra-internode communication. This is something that most algorithms fail to achieve. Other than that, the proposed design uses the least number of QPs per node. It uses the least number of send operation per node. We also did some performance study to study the how well it can scale compared to UD. It's where the proposed design also maintain all of the reliability of RC. Other than that, the design is network agnostic. It can be applied to any RDMA network. And we have used InfiniBand, OmniPath as a case study in this paper. So the proposed design, it has 3 versions. In the first version, we call it a naive design. So for this version, the key idea is to reduce the number of QPs or the number of connections being used during the communication. This is a 2-phase design. As you can see in this diagram, in the first phase, in order for the process leader to communicate on behalf of other local processes in a node, the local processes we need to copy data into a share buffer. We call it share send buffer, right? And in phase number 2, the process leader here, P0, can just invoke a network operation and send data on behalf of other local processes. We realized that when the network operation happening, the local CPUs, they are idle, right? They do nothing. So we can overlap the network operation with the memory copy in this phase. So this diagram demonstrate in detail how we copy data from the send application send buffer into a share region so that the leader can read from it and perform the network operation. So the green zigzag here is the memory copy order into the share buffer. So one thing that I want to emphasize here is that we did design a process, the process leader will need to send 2 operations to a remote node to exchange data. In the second version, we focus on the performance. For this version, we try to reduce the number of network operations to only 1. We only need 1 network operation to communicate with a remote node. So the key idea of the second design is request coalescing. That is the technique we use. We reorder data differently in the second version so that we only need 1 send operation to communicate with a remote node. In the last version, we realized that in the previous design, we used more shared memory than we needed, which is not good. So we will try to reduce the memory footprint in the previous design. So essentially, in the previous design, we will need the number of node times the number of data block size for a share receive buffer. A data block in this paper, it defines as the number of data received by a node from another remote node. We realize that we only need 2 times the data blocks here. We only need 2 data block size. So as demonstrated by this diagram, in one phase, one block is used to receive the data from a remote leader. Another block can be used to copy data out. And in the next step, we reverse the role of these 2 blocks, right? We alternate between these 2 blocks for the operation. So in summary, this table demonstrates the analysis of the proposed design going from version 1, 2, and 3. So essentially, in version 1, we focus on reduce the number of connections we need per node. On version number 2, we focus on reduce the number of network operation. And in the last version, we focus on reducing the memory footprint. So now let's move on to the performance evaluation. So we study the performance of the proposed design on 2 clusters. The first cluster is an infinite band cluster. The second one is an omnipath cluster. So we also perform an exhaustive study. We compare with existing MPI libraries, for example, like MFABH2X, sorry, Intel MPI, OpenMPI plus USEC, and XBCX. So in the first experiment, we compare all 3 versions of the design. We also compare with state-of-the-art auto algorithm. So the final design V3, it is the gray column here. It outperforms all of all the version of the proposed algorithm V1, V2 in all of the messages, in all scales. Other when compared to when we compare the final design, the V3 design, to other state-of-the-art algorithm, the proposed design also outperform any other existing algorithms. So in summary, the final design outperform the flat algorithm here. This is because it's good for small messages by 40 to 50%. And it also performs better than state-of-the-art hierarchical design by traps and chokeholds by 9 to 50% on average. So the next set of numbers demonstrate the performance of the proposed design when compared to existing MPI libraries. So we perform the study scaling from a small amount of processes to the largest scale possible here, up to 7,000 processes. So in this figure, you can see that the proposed design is the dark blue column here. It outperforms all of the existing MPI library for different messages right here. All right. So in summary, on the largest scale possible with 7,000 processes, we outperform from 35 to 60% on average better than OpenMPI plus UCX, SBCX, Intel MPI, and MFABH2X on an infinite band cluster. So like I mentioned earlier, the design is network agnostic. It can be applied to any RDMA network. And this chart demonstrate the performance of the proposed design on omnipath cluster, and we observe a similar performance a similar trend as with InfiniBand cluster. So we also demonstrate the scalability of the proposed design. We compare the proposed design with different transport protocols. So as you can see here in this chart, the blue line here is the an algorithm that pick the best transport among the three transport protocols that I introduced earlier, depending on the message size, process count. We scale from 2 node, 56 ppm up to all the way to 128 node, 56 ppm, which is around 7 or 8,000, up close to 8,000 processes. And you can see that the proposed design outperform by up to 60 to 70% better for 512 1K byte auto when compared to the multi-transport tool algorithm. We also demonstrate the performance improvement at the application with CBMD. So CBMD is a molecular dynamic application. It heavily utilizes auto for the communication for the simulation. We see from 25, 40, 50% better in performance when compared to mFab2x, OpenMPI, UCX, and Intel MPI. So in summary, we propose a high-performance, scalable, network-aware auto design. We also demonstrate the network-agnostic property of the design on InfiniBand and OmniPath. We thoroughly evaluate with various MPI implementations like Intel MPI, OpenMPI, SPSX, and mFab2x. We also done the scalability study of the design again, different transport protocols, RC, DC, and UD. We'll finally demonstrate the benefit at the application level with CBMD. With that, I conclude my talk. I'll be happy to answer any question.
Fantastic, too. That was great talk, great work. There are a couple of questions in the Slack channel, and I'll queue those up for you. I'll just read them out for you. One is from Pankaj Mehra saying, did you evaluate your version 3 versus HPCX with the shared memory transport layer? Or did your focus on RDMA rule out that particular transport layer for HPCX?
Based on your question, I assume that you want me to enable a specific like environment or setting in HPCX, and that we haven't done. So essentially what I did was I run the SPSX, whatever the performance out of the box by SPSX. We didn't exactly tune SPSX when we compare this. I hope this answers your question.
Thanks. Let's see, one more. Beyond some all-to-all message size, aggregation algorithms begin underperforming simpler non-aggregating algorithms. Everything that you showed today was far better. Did you go ahead and push it to the limit and see what was that max message size, where you start crossing over and wish and just go back to the more mundane algorithms?
Yes, I seen this when we have like designed this. So this is like common concepts. Memory copy will work really well when the message size is small, but as you increase the message size, you likely to see that hierarchical design will perform worse than flat algorithm like pairwise. So in this case, to if you want to continue to exploit hierarchical for larger message size, you need some kernel solution like zero copy design, like CMA or XPMM. That's one of the future work that I am trying to pursue.
Yeah. So, and my question here was, without changing anything, did you happen to see where that crossover point is now? Whether it's 4 kilobyte or
Right.
whatever.
Yes, it is application. Sorry, it is cluster specific.
Okay.
Not exactly. Yeah. So essentially, you will see the crossover over around 1K to 4K. That is the
Okay.
range that I expected.
Very good. I don't see any more questions in the Slack channel. Let me just make sure that nobody posted. Yeah, it looks like we're good. This is great work. This is really, hitting the mark, obviously, for, when you have all-to-alls of small message sizes, and hope to see it get into Mbappage as part of the regular distribution at some point. Thank you. Thank you very much.
All right. Thank you.
Virtual round of applause.